Friday schedule, and I think impacts the amount of AO time you have. With Friday Creative Options, some of you guys will have projects that extend outside of that class that aren't necessarily required, but you'll probably want to work on them because they'll be fun. We have May term coming in Q4, which that Q4 gets easier than Q3 because there's a lot of crazy stuff going on in Q4, including travel and everything else. But please take my advice, maybe, if you decide to. If you struggle to keep up with homework on the normal, like Q1 and Q2, you should try to work ahead, and you'll have an entire day, potentially 2, that you could do so. You're very welcome. So you might jot down a few of those homeworks. I had a student the other day ask me if I wanted to bring my phone down and take a picture of that. I said, yeah, that's fine. Grab it like at extensions or something, come down and take a picture. One of the kids I tutor, he keeps all his homework on his phone. Now, when his phone is dead, that's an absolute issue. But yeah, it is an option. Yeah.
Why do you keep saying Q3 is harder? That hard for me.
We're just getting into it. Also, we've rearranged some things because we identified Q3 was so difficult. So what I should really say is, in the past, Q3 is always the toughest for most students to keep up with their work and stay mastered. And we have higher mastery expectations. I'm going to give you guys your test back when we have time to process them all together. And honestly, I didn't even get to grading Dave's. But a lot of you have progressings, and a lot of those of you might be used to having masteries on your math tests. We up our expectations is also, Quinn, why I say it's the toughest quarter. We know you, and we know where you should be performing. So this is kind of the double-edged sword of Phoenix. As we get to know you better, we have a more accurate expectation of where your mastery line should be.
So it was a trap.
Kind of. These are not the drones. Wait, what? Or I mean, yeah. No. So if you want to make a quick note of the next assignments, so today's 58 to 63. I'll just go ahead and even type this here. The next one is 70 to 75. This gets really easy. The next one is 80 to 85. Yeah, it's pretty much just the review preview. A couple of them get modified here and there, but I think all the next ones, we're just doing all of them because they're really good practice. Those are the next batches of homeworks. That takes us all the way through Chapter 6. So if you want to have, now, in Chapter 7, we do skip a decent amount of stuff. So, if you're going to start Chapter 7, we skip all of 7.1. Okay, so be aware, if you're going to start Chapter 7, we skip all of 7.1. Any other questions before we dive in? It's going to still be up there, don't worry, it's just on the TV. So, as you guys walked in, well, as some of you guys walked in, I was speculating that I don't necessarily trust what we did yesterday. So, yesterday we were talking about what happens when I switch the places of the X and the Y. So I want you really quickly make a little 5x5 grid, out to +5, out to -5, and then up to +5, down to -5. Really quickly make that. And we yesterday were speculating if I take X, Y, and switch the location of them to essentially make it YX, which of course we know it won't be YX, it will still be in XY. Now this should be on your graph paper, guys. So you should have a piece of graph paper, you should be making a little 5x, ignore the lesson right now. We're picking up yesterday's work. Ignore the lesson and the resource page. You need a piece of graph paper out right now. I want you to make a little triangle, and don't make it all 1, 1, 2, 2, 3, 3. Make them some unique points, 1, 4, or 2, 5. Don't make the numbers match. If you make the numbers match, it's more complicated. Test this out. If we take all the points of a triangle, X, Y, and just reverse their locations to make them YX, what is that transformation? I'm going to give you a couple minutes to do this. So make your own triangle on your paper. I'm going to do one up here too. But do your own thing. You don't need me.
But yes, we do. We need you to grade our homeworks and our
Nah. actually, we'll talk about that probably here after the snow day. You guys are going to be able to check all your own homeworks here in quarter 3. Yep.
Is this ball mace thing?
What? Hey, Connor, we're in the middle of class. So do you think that's an appropriate thing to be putting your attention on right now? Yes, it is a 3D maze ball that, yes, I've gotten out because now we're further into the year and I want to give you guys some things to play with. But no, you cannot do anything with it right now. Later, absolutely play with it. Now, I will warn you, it's broken.
Dang it.
So you'll realize if you start to play with it, it is broken. You can still do it. There's one part of the map, I think like 40 or 50 some steps into it, that you can't necessarily, you have to like jump a gap, and it's really tough. No, you're supposed to be making your own triangle. I already gave these directions, Quinn. You don't need to be copying me. You need to be doing your own thing.
Wait, does it have to be on one corner?
No. You are just doing your own thing. Whatever triangle you make, switch your X and Y coordinates and make the new one. Doesn't matter where you started. Doesn't matter where you end. Switch. So, this is -1, 1. I'm going to flip their places, make it 1, -1, and my A prime comes here.
Oh.
I'm going to switch my places for my B, and what was -1, 3 flips to 3, -1, and becomes my prime point. Likewise with C, I flip my places, and that becomes my C prime. Now yesterday we speculated that was a reflection. XY going to the YX. And guys, I'm going to warn you, as you get deeper up into your math study, your teachers will sometimes set traps for you.
It's a trap.
And they will speculate something, and if you are not paying attention and you blindly go with it, it's wrong. Because we're trying to see if you are thinking. Now, yesterday with the fire drill and everything else, we kind of ran out of time to come back to this hypothesis that we had. So you should have your own triangle, a pre-image, and an image. And I forget, actually, I should really go back to yesterday's lesson and see what it was speculating. I just wanted to make sure we cleaned up our rules. Yeah.
I don't really, like, what are the different lines? Like, I don't know what the negative or positive is.
So, I will come back to that in a second. So just to bring us back to where we were having a lot of what happens if questions yesterday. Right? What happens if, what happens if, what happens if. And I think the one that we left on was what happens if I multiply them both by a negative. So here I switched my X and my Y. Grab a different color. You should have colored pencils. And what happens if we switch X, Y, or sorry, not switch, we did just switch. What happens if I multiply and make it -X, -Y? Crud. I moved it. On the same graph. So now, +1. Wait, A is in the same location. At least for me.
From the original one?
Still from the original.
Oh, the original.
Sorry, still from the original. This is why this is so dangerous. look at how similar those triangles are to each other. My blue image versus my red image that are like on top of each other. Yesterday, you all allowed me, and it's not your fault, I set this up on purpose, you allowed me to not on a graph, right, no coordinate grid, slop up some triangle ABC and flop it over here, and I actually changed, I first labeled CB, then I was like, oh wait, no, BC, and nobody really thought anything of it, and nobody really pushed back. And guys, I want to encourage you and give you the power, push back when things don't seem quite right, or if it doesn't make 100% sense. If you walked out here and you thought like, oh yeah, that makes 100% sense, I know that you were lying to yourself. This doesn't make 100% sense to us yet, because this is tough. Which one's which is a dangerous game up here. The blue image switched their places, right? Pre-image to image, blue switched places. XY became YX. What is that? Is it a rotation or reflection? Who can tell me?
I got it.
Raylan? The blue to blue? Not. Because if I rotate this, B is going to point down, and in blue, C points down. Quinn?
I got something a little different from your theory, but what I'm confused is, so your blue image, you did Y and then X, but how would you get all the way down? Oh, that's because you were using negatives.
I use positives and negatives. But if you use all positives and you switch their locations, the same thing happens. It just looks totally different than this one, but the same event happens. Guys, this, the blue, the switching of the XY, I want you to check your notes from yesterday because I think I might have let you write down the wrong thing because I was trying to set up a trap door and then it didn't happen. We had a fire drill. This is not a rotation. That's a reflection of the XY. But yesterday, I'm pretty sure what we wrote in our notes was this. The whole if we multiply by -1, we called that a reflection. It's not. That's our rotation of 180 degrees. So here's the rules we want to make sure we get down. And they're all here for you, and I'm probably going to laminate this. When we are rotating, here's my pre-image. Actually, I'll bring this over here for right now. Oh. Lame. When we are rotating, clock, you were in the way. Pre-image. Right now, it's nice to use positives and negatives because it can help you keep straight like what did what. If I rotate 90 degrees, and this is the negative direction, but it's still 90 degrees, I got to switch places and a sign, right? We saw that through our investigations. If I rotate 90 degrees this way, I switch places, X and Y, and I switch a sign. If I rotate 180 degrees, I switch both signs. We switch both signs. Every rotation has a sign switch happening. Either if you're going one quadrant, one sign switches, or if you're going 2 quadrants away, both signs switch. But this red image was when we swapped X for Y. See that green line on there? The line X equals Y, or we also call it Y equals X, which is circling back to, I forget who asked, like I don't understand the lines. This line is Y equals X, and I want you to draw it on your notes real quick. That, and this should make sense in our brain, says your Y is now your X is now your Y, because Y equals X and X equals Y. If we reflect the green line, we come to blue. goes to B prime, A goes to A prime, C goes to C prime, directly across that diagonal line. So before we dove into our dilations today, I wanted to circle back. And really, here's what you need to remember. Every rotation involves a sign change. This reflection switched your places. X and Y just trade locations. Now, there are other reflections, as we looked at through our investigations. If we just reflect the y-axis, the y changes sign. If we just reflect the x-axis, the x, or, no, I got that backwards. If we reflect the x-axis, the y changes sign. If we reflect the y-axis, the x changes sign. So don't tell yourself every sign change is a rotation. That's not a rule we're making. We're just saying every rotation has to have a sign change. Okay? I would advise you to either come study this, and I'm going to get this laminated and like it'll just become a poster in the classroom, / alternative option. If you Google rotation and reflection rules, they're real easy laid out here. If we reflect the x-axis, the y switches sign. So I'll zoom in even more because I know the smartboard's not that big. If we reflect the y-axis, the x changes sign. If we reflect across the line we just looked at, my places trade. And this little symbol means like becomes or goes to. Do not think that's like a negative less than, like that's just being used as an arrow. So here's what we just talked about. This 90-degree rotation. This is also a 90-degree rotation. Notice they trade places and a sign, and then the 180 just totally switches sign. Because you're working on your practice and you need to Google this, that's totally fine. At some point, you might want to get this into your notes to help that solidify in your memory. Questions before we move on to our actual lesson today? Quinn?
How do I know that you're not telling another lie?
This is not a lie. This is not a trap today. This is
sure?
Google supports me. So yes, you can be sure by. And there's also some really good image explanations. You can find some involving a coordinate grid. This is also an now be careful. They talk about clockwise versus counterclockwise here. So that can actually help you with positive, negative. But yeah, we need to move on for today then. Any other questions about that? And I'll even put it up on the chalkboard. So we said the reflection across the line. What happened to xy? Becomes yx.
Yes.
What about the rotation 180?
Negative x, negative y.
And they don't trade places?
No, they don't.
So just trade places, just switch signs. Question, are you stretching? Okay, I'm guessing you're stretching. All right. So we are going to help Charlie. Charlie Mamlin was a great student of mine a couple years ago. He was the kid, if you saw that crazy basketball like three-pointer or whatever that like won the game in the Cardinals versus Wolves last year, 2 years ago. Okay, maybe you guys don't care. There was a sweet like end of the game like half court shot that he made. It like floated around Twitter or whatever, Instagram. So you have this on your paper. And if you start to list out what the coordinates actually are, you'll notice something interesting about the locations. And actually, I have it up here on my graph paper too. I'm going to do this as we go through it together. So I would like you first, at each coordinate, just kind of jot down what it is. So if we go up to this coordinate, it is 4, 8, right? So we could write that. So go ahead and label each of your coordinates. Oh, we're noticing something. Go figure.
It means I have eyes.
We're all positive negative 4s and or positive negative 8s, right? What kind of shape is this? Trapezoid. Now, we could use a mathematical formula to figure this out, but this line, we can see on the graph, follows the intersections. Boom, 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 boom. So does this one. So we can see that they're parallel, which makes this a trapezoid. So what Charlie has here is the result of a dilation. And I need to use more cards. Jessica, what did we say a dilation was? Compression or what's the other way? Ooh, shrink is the same as compression. Stretch, right? Or expansion, right? So compression or expansion, compression or stretch, whatever you want to say. So what Charlie has there is the result of a dilation of 4. If that was what he did to get this shape, how do we undo the dilation and make that happen on your paper? So essentially what I'm asking you to do is find the pre-image if we know this is actually the image, the after dilation.
So he multiplied everything by 4.
He dilated by 4. That is what he did to make this shape.
Okay,
So how do we undo his dilation and make that happen? And you could use like, a certain color to make this happen if you want. That's why I have you having colored pencils.
I think I did a thing.
Yeah, sorry, this is on the resource page now, guys. So that's why I said you have this on your paper. I did not really draw this on your paper. Like, you have this on the resource page.
I found it.
So if 2 dilate, we multiply by a scale factor. How do we undo dilation? Ooh, divide, because that's the backwards operation.
Yeah.
And it's made up for what it's worth, but we'll let it fly for right now.
Pseudo-mathematics.
Oh, smart board.
The
Come
smart
back
one
in.
being smart.
No, it just like cycled.
Cycle. Cycle killer.
Yeah, it's glitching.
Cycle killer.
So, here's something interesting. Here's the origin, right? The 0, 0 point. And our shape goes through that. And unless we're told otherwise, our origin is going to be the center of dilation. And when I shrink down my negative 4, 4, and divide this whole thing by that scale factor of 4, what do I end, like? Where do I end up at? Anybody?
Negative 1.
Negative 1, 1. Ooh, it's on the same line. And then my 4, negative 4 point becomes
1, negative
1,
1.
negative 1. My 8, 4 point becomes
2,
2, positive 1. And my 4, 8 point becomes
1, 2.
1, positive 2.
That's some pretty straight lines you got there.
Now, just for fun, if this, and if you can write it right in here, this is our pre-image. And this was our image using a scale factor of 4. Just for fun, draw the shapes of scale factor 2 and 3. And 5 if you feel like it. Just for fun, but I would like you to do it. Draw the shapes of scale factor 2 and 3 and 5 now that we have the pre-image. To go and do something, we must know where we start. So now that we have the pre-image, we can.
Now we can conquer the world, but just as planned.
Thanks, Quinn. And I got the talking head stuck in my head. There's a band named the Talking Heads, and the song he was singing is from them.
Oh no, what have I done?
So, scale factor 2,
Oh, I am right.
right?
Woo.
This gets fun because it's like ripples in a pond sort of thing. Except it's not going out every direction. Why aren't we expanding on this baseline?
I didn't do it right.
Why doesn't this edge move?
Because it's on the origin.
Yeah, and here it's on the blank of blank. Center of dilation.
Oh.
If an edge goes through your dilation center, it's going to stay where it is. It's going to change size, but it's going to stay where it is. Get some purple going on over here. And then 5, where's that going to land? It's going to be on the outside, right? So it's going to go like 5, -5. Did you notice that the shifting that's happening on all of these is the same? Like the L's that get created? If I bump out 2 and up 1, that's what I do every new scale factor. Out 2, up 1, or out 1, up 2. Out 1, up 2, out 1, up 2, out 1, up 2, out 1, up 2.
That sounds like
The same thing happening. So over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1. 1 up. And there is my scale factor of 5. So now move on to 53, the graph that you have on the bottom of the front of this paper. Alana has been working with a scale factor that's actually a fraction. So Alana says, I wonder what happens if I multiply each coordinate by a fractional value, like 1/3.
Oh no.
So
we don't.
these points, put those points on your 53. This is the image, not pre-image. This is the image after dilation. So this that you're putting on the bottom graph, you're not using the same graph, this is the image after dilating. What we need to figure out is the pre-image. Take a minute or two to do that. Those points we have are the image. We need to find the pre-image.
So this is a confusing.
Sorry, I'll zoom in more. Sorry, my circle's not in the right place now, but -1, -1, -1, 1, 1, 2, 2, -1.
2, 2, 1. Yeah. This is a pretty funky looking shape, if I say so myself. So I'm not going to say what we're supposed to do.
This shape has been multiplied by 1/3.
I know I think it's right.
So the image is the result, right? So there's what kind of shape do we have? Yeah, awkward quadrilateral, right? Or like a weird house. You might find some houses where you have like an angled wall of windows, something like that. That could be a cool design. If this is the image, it's the result, right? Now, Connor was just saying, well, yeah, again, we divide. Now we're dividing by 1/3, or we can just times by 3 because dividing by a fraction makes me want to throw up. So, I'm not joking, guys. The idea. So, imagine this for feeling like you're going to get fired. I was at the WEC, right? Not actually like I would get fired, but I was at the WEC talking with one of my bosses, and he's the math boss. And he's sitting there with Brian Genius, the guy who came and talked to us about science fair, and they have a whiteboard in front of them. And they say, Micah, can you model for us division by a fraction?
No.
And this was like 2 or 3 years ago. And I was like, yeah, sure. Like if I have a pizza and they're like, no, you divided by 4 or something. They're like, you didn't divide by a fraction. You cut it into fractions. I like try again. And finally I'm like, you know what? I probably can't. And this was before CPM and before we adopted this new curriculum. And they were looking at how CPM approaches the idea of dividing by fractions. If I have 6 pizzas and I divide into groups of 3/8, the result is the thing that doesn't make sense, right? Because the result is how many groups, like how many plates of pizza. So it's very hard to conceptualize, and that's why we would rather multiply by the reciprocal. So to undo a dilation that was shrinkage, we obviously are going to get bigger, and this becomes my pre-image, which, as Jessica said, is larger than the original. Now I have a challenge, and I don't think it's in the book. Could we dilate to a new image from this pre-image with a scale factor of 3 halves?
Yeah.
Test it out. Could we dilate with a mixed number or an improper, right? Because that's either. It's mixed or improper. Try that out. Going from red, from your pre-image, can we do that?
Oh, that's easy. Yeah. I did it.
Well, make it happen.
Yeah, just give me a couple minutes and it will live.
Or can we not use a decimal? So there's a couple points here that should be easy to deal with, and a couple that aren't as easy. If my point out here is 6, -3. What's 6 times 3?
6 times 3, 18.
Divide that by 2.
9.
9, that will actually work. I'm going to have an x value of 9. Now, my y value, what's 3 times 3?
18. Wait, no, 3 times 6, 9.
Divide that by 2.
Sure.
4.5, and we know it has to be negative. I'm going to be just between. Nothing says my points have to land on intersections. So then, that's what I do with every number I have. Multiply by 3, and then divide by 2.
I got it.
Oh, that makes sense.
So, my 3, 6, well actually, I'm working with the same numbers. Make your life easy. This will be, instead of 3, 4.5, and instead of 6, 9.
Mr. Person, a way I found it easier is just divide by 2 and then add it to the
Yeah, you can do that too. Cut in half and then multiply by 3. And then the 3's, -3, +3, or +3, -3, either of these. Or, sorry, -3, -3. We know those both just turn into 4.5s, although they're negative. Anyone know why I didn't have you use a scale factor of 2?
Because if we doubled it, it would be too big.
It would not fit on your graph.
Too big. Also, cool demonstration.
Yeah, you can multiply by any scale factor you want.
It's just
Now, I will tell you, scale factor, because it's changing size, it's being used as a multiplier. If all we're doing, hey guys, I'm trying to like let your conversation take its course and then come back to me, but you're not coming back to me, so like that needs to happen. If all you're doing is changing size, we cannot use negatives. I will leave the question in your brain, what if we used a negative scale factor, which we know we can't technically, but what if I multiplied every coordinate by negative 2? Instead of 2, just what about negative 2? What do you think? We're not going to go down that road today. What do you think would happen? Just put that in your brain. All right, now, on the back, flip over to the back, please.
Oh, no.
So we're now looking at this.
I don't like it.
And I'm going to leave this not with your team, but on your own. Take the next 2 minutes, play with this, draw some stuff on your paper that then when we come back together in class, you could challenge people of, okay, try this. Okay, try that. Like here's a random question. What's the biggest scale factor we could fit on this page? If this is your pre-image, what's the biggest scale factor we could use? Or you could try what happens if I use a negative number scale factor. Like, what is that? Like, play with this for a couple minutes. We only have a couple minutes left, but we will dive back into this the next day we're together in class. Right now, I just want you to kind of goof around on your paper, draw some stuff. And people watching from home, Savannah, feel better. Aside from that, this is it. That's all we're doing today.